Okay, so yesterday we left off with the with question number 5, where we calculated the final position of the person, okay, given their displacement and their initial position. Okay, now I want you to try number 6. Okay, number 6, mathematically very, very simple, but you do need to read it carefully. Okay, because a lot of people make a very simple error on it because they don't read it carefully enough. Okay, so I'm going to give you a few minutes, read it, give it a try, and then I'm going to solve it on the board. Okay. All right, so we've got this, we're essentially tracking the trip of the ball, okay, as it goes from one person to the other. Okay, it says that it starts with the person on the right. It says the person on the right tosses the ball to the child on the left. So that means this is our initial position for the ball. Okay? The ball then travels to the person on the left, who then hits it back over this person's head, and they have to go running over here to get it. So this is their final position. Right? So if I want to find the displacement, well, displacement's pretty easy, right? Displacement is final position minus initial position, so that'll be essentially 5 meters to the right? Like this is the initial, there's the final, it only goes 5 meters. Okay? Everybody all right with that? We'd say our initial position is 0, and off we go. Now, for the distance, how far does this ball go? Yeah, that's the gut reaction, 8 meters. Is it really 8 meters? It's 11 meters. Here's the thing, this is why you have to read the question carefully. Okay? The ball doesn't go from here to here. It goes from here to here and then over to here. That's 3 plus 3 plus 5, that's 11. Okay? It's easy to miss that, right? Because we just look at the numbers are already there. I'll just add them together. 3 plus 5 is so easy. Okay? But we forget that there's a little extra step there, that the ball traveled that 3 meter distance twice. Okay. All right. Now, in terms of manipulation, okay, you're in Physics 20 now. Algebra is a big deal. Okay, you're going to have to be able to manipulate equations easily and quickly. All right. I don't want to see this. If you're manipulating equations with triangles, your life in physics is over. There's no nice way to say it. Okay, that formula will work just fine for this form, or that triangle will work fine for this formula. But what are you going to do when we get into Unit 4 and you got to manipulate that puppy? There ain't no triangle for that. Not even a rhombus is going to help you there. Okay, got to learn how to manipulate equations, because a triangle is not how you do that. I know some well-meaning person along the way taught you triangles, but they crippled your math abilities for life. Okay, and it's bad. Please, we have to learn how to do actual algebra. Okay, remember the 3 rules of algebra. Very simple. Okay, if I want to move something, I do the opposite. What I do to one side, I do to the other, okay, and I move what's not attached to what I'm looking for first. That doesn't really apply to this formula, but this one that we'll be using later on, okay, which you saw in math, I'm sure, okay, y equals mx plus b, okay, if I want to solve for m, what do I move first? B, it's not attached to m, okay, those are the 3 rules of algebra. They're super easy to follow. Guys, those 3 rules got me through university physics. Okay, they will help you with your algebra and with your math. They'll get you through high school physics for sure. Okay, there's nothing overly difficult about the math that we do. We just have to be able to do it. Okay, and if we're using crutches like a triangle, it's just not going to work for you past today. Okay, so I just want to save you that agony. Okay, later, right? Discovering, oh man, I really need to know how to do this. I can help you with that. Okay, I can help you with the algebra. Okay, come in and see me, and we'll make that work. Okay, sometimes we're going to run into v equals d over t problems that are like this one, that have more than one part to the trip. Okay, when we run into problems like that, here's what we have to remember. V equals d over t actually means this. average velocity equals total displacement divided by total time. Okay? That way we can account for a trip that has more than one part. Okay? There are some things that we have to do separately for each part, but when we're talking about the total, okay, we put it all together. Right? We don't average it after. Okay? Because people get this idea as soon as they see average. Oh, I know how to calculate an average. I add all the parts and then divide by the number of parts, except that that's not true if the parts don't represent equal amounts of the whole. Okay? It's fine for calculating a class average in here because you all represent an equal part of the whole class. But if I'm talking about a trip to Edmonton, let's say, where I drive at 120 kilometers an hour for 295 kilometers, and then I drive at 50 because there's road construction for the last 5 kilometers, is my average, okay, 50 plus 120 divided by 2? Or did I travel at 120 for a lot more of the trip? And thus my average should be a lot closer to 120. Okay? It should be, right? I have to weight the average, and we don't do that if we're just adding them together and dividing by 2. Then we're saying, hey, half the trip was this and half the trip was that. Okay? That's another one of those North American things that we do that's bad. Okay? Oh, yeah, that half of the trip was awful, when it's like 10%. Okay? Not really bad. All right. I'm going to give you guys a couple minutes and see if you can do this one, okay, before I do it with you. You would have done ones like this in Science 10, okay, 2-part V equals D over T problems, right? I will tell you this, break it up and write down your givens for each part, and then have a column that's totals. So I would start it like this, okay? Part 1, write down what you know for part 1, okay? Part 2, write down what you know for part 2, okay? Then have your totals. Okay, remember that to calculate the average velocity, you're going to need the total displacement and the total time. That means you'll need the displacement for each part and the time for each part. Okay. And for speed, same idea, except average speed is total distance over total time. All right, give you a couple minutes on that one. So the first thing we want to do is write down our givens, okay, what the question tells us about this trip. Okay? So the first part of this says that it travels at 4 meters per second north. Okay, so I know the velocity is 4.0 meters per second north, and it does that for 12.5 seconds. Okay, and then it tells me that in part 2, it travels 26 meters south, and that it does so at 16 meters per second south. Okay, so that's the information I have. If I want to calculate average velocity, I need the total displacement and the total time. That means I need the displacement for both trips and the time for both trips. Okay? And I don't have that right now, but can I find it? I can. I just have to use V equals D over T. Okay? So I'm going to use V equals D over T in part 1, but I'm going to solve for D. So I'm going to multiply both sides by T. So V times T will equal D, and I'll get 4 times 12.5, which should be 50 meters. Okay? And that'll be north. All right, so now I know my displacement in part 1 and in part 2. All right, I don't know the time in part 2, but I can find it by manipulating V equals D over T. I'm going to bring T over here and then divide V back over. So T will equal D over V. That'll be 26 over 16. That one I can't do in my head. 1.625. 1.625? Okay. That's all the decimals?
Yeah.
Okay. Okay, 1.625 seconds is my time for part 2. All right, well now I can calculate my total displacement. I've got 50 meters north and 26 meters south. Okay, what's my overall displacement? 24 meters north. Okay, I've got 12.5 seconds and 1.625 seconds. So I've got 14.125 seconds, is that right?
Yeah.
Okay. As my total time. All right, can I calculate my average velocity now? I can. Okay. So if I do that, my average velocity will be 24 over 14.125. Oh, not 14, 24. All right, so we're looking at 1.7 meters per second north. Okay, is that a lot different answer than I would have got if I'd have added 4 and 16 and divided by 2? A lot different. Okay, even if I'd have made the 16 negative, it still would have been a lot different. Okay, that's why I can't just add them together. This part 2 represents a lot smaller chunk of the trip than part 1 does. Okay? Part 1 happened for 12.5 seconds. Part 2 only happened for 1.5 seconds. Okay? It's considerably bigger parts of the trip. All right, that's part A, because they wanted us to calculate the velocity. Now I need to calculate the average speed. Okay? So average speed is total distance divided by total time. What do I do differently? Right, I don't pay attention to the direction. It doesn't matter that one is north and one is south. It only cares how far did I go in total. So 50 plus 26 is 76 meters, okay? And that still happens over the same amount of time, 14.125 seconds. All right, so now our speed is 5.4 meters per second. No direction on that, because it's a scalar quantity. Right? Is that making sense to everybody? Okay. It's an easy mistake to make, okay? And people fall into it. As soon as they see average, they go back to how they were taught to calculate averages, which is fine if everything is equal. Had this trip been, they did part 1 for 12.5 seconds and part 2 for 12.5 seconds, you could have absolutely added the two together and divided by 2. Okay? But that never happens. Spoiler alert, it just never happens. Okay, so you're going to have to do this weighted average, total displacement over total time, or total distance over total time. Okay. Any questions on that? Okay. That's as tricky as a V equals D over T vector scalar problem would get. Okay, so it's not very tough. Okay, what becomes more difficult when we start getting into vector addition and we got angles and stuff like that. Okay, that'll be a little bit different. All right, what I want you guys to do is I want you to try a few of the V equals D over T problems out of the workbook. They're really easy. Like, we're not going to spend very much time on that, just a little bit of practice, and then we can go over any ones that give you trouble. Okay, but I'll call those up right now. Okay, so we're in the class work tab, notes and worksheets, okay, and we are looking at 21. I got a 50-50 chance, did I guess right? I did. Okay, so I want you guys working on, okay, the ones here that start on page 2. Okay, you can just pick a few, but don't go past number 8, because actually number 8 even asks about graphs. Number 7 asks about graphs, but you can do number 7. Just don't worry about the graph. Okay, we're going to talk about graphs later on. Okay, we don't need to worry about graphs for right now. Awesome. Yes. Okay, I'll give you a few minutes there, guys, to work on those. If any of them give us trouble, then just ask, okay, and we'll go through them together, okay, if there are any questions. Okay, so for number 6, okay, they're telling us information about both the sloth and the tortoise, right? Yeah. Okay, so we've got the sloth here, okay, that moves at an average speed of 0.037 meters per second, okay, so that'll be the sloth, okay, and then we know the speed of the tortoise as well, that is 0.076 meters per second, okay. How much further will the tortoise have gone relative to the sloth after 12 minutes? Okay, so the trick with this question is, I'm given time in minutes, but here I'm given velocity in meters per second, and I gotta make my units match. Okay, so I've got to take that 12 minutes and multiply by 60 in order to get my actual time in seconds, so my units match. So each one of these is going to be 720 seconds. This one's going to be 720 seconds. That's the whole purpose of that question, is just to make sure, to remind you that something happens in Science 10. Our units always have to match. Okay, so once we've got those matching, then it's just a matter of d equals v times t, and d equals v times t, and then we've got that the tortoise will go 28 meters further than the sloth. Right. Any other ones giving us trouble there before we move on? Okay, cool. Then we're going to look at lesson 3 here in your notes package. Okay, we're going to look at addition of collinear vectors. Okay, we're also maybe even going to get to perpendicular vectors today, okay, which would be something new. Collinear vectors you did in Science 10. Okay, they're ones that are along the same line, one-dimensional, north and south, right and left. That's collinear. Okay, when we get to perpendicular, that could be a situation like, it goes north for 100 meters and then turns and goes east for 50 meters. Okay, and then we would have a right-angle triangle, and we would have to do a little bit of trading. Okay. All right. So first off, what are collinear vectors? They are vectors that are along the same line. Okay, they share a line, collinear. Okay, all types of vectors are added by placing them tail to head. We actually talked about that on day 1. Okay, we always draw the diagrams like we're telling a story. First it did this, and then we put the next one on the head of that. It did this next, and then this. Okay, and understand that vector quantities obviously have magnitude and direction. We reviewed that yesterday. Okay, and all vector quantities, regardless if it's displacement, velocity, acceleration, force, doesn't matter. They're all added the same way. All that changes is at the end you have different units. Okay, so if it asks me, here's a force and here's a force, add them together, okay, my resultants, okay, will be in newtons instead of in meters if they were displacement vectors and so on. But they're all added exactly the same way. Draw them tail to head, add them together, okay, and you get your answer. All right, questions on that so far? Okay. All right, so talking from yesterday, okay, a vector is a quantity that deals with both magnitude and direction. Okay, direction is an important characteristic, so we represent all vectors with arrows. Okay, that's the common kind of method for representing any vector quantity. We draw it as an arrow. The length of the arrow represents the magnitude of that vector quantity. Okay, so if I had a 5-meter long vector and a 10-meter long vector, the 10-meter long vector should be twice as long as the 5-meter long vector. Length represents magnitude. Everybody okay with that? And then obviously, since we're drawing an arrow, we want it to point in the direction that that vector is supposed to be going. Okay, so that's basically the whole reason we use an arrow, is so that it points in the direction of the given vector. All right, so the direction of the arrow gives the direction of the vector, and then the length of it. Okay, so if this is a 2-kilometer vector, a 1-kilometer vector, okay, would be only that one. Okay, that's pretty straightforward. All vectors are drawn using that convention. Okay. All right, so like I said here, logical to use the length of the arrow, okay, to represent the magnitude of the vector. Okay, so length of the arrow is proportional to the magnitude. Now, lots of times it's necessary to add one vector quantity to another. If they're collinear, you probably don't need to draw the vector diagram. I mean, realistically, why would you? Okay, you can add or subtract without a picture to help you with that. Okay, so I wouldn't expect that if someone said the car went 200 meters east and then went 100 meters east, solve this and just actually see you draw a vector diagram of that. You wouldn't need to. Obviously, it's only 300 meters. Okay, it's more for complex vectors that we would have this, but we use this just to show you this is how we actually draw them. All right, so in this first example here, okay, our car moves 275 meters due east. Okay, so that's this first line right here. That's our 275 meter long due east vector. When we draw these, okay, we usually write above or below them, okay, whichever is convenient, okay, the magnitude of that vector, right? Now, when I'm drawing vectors, if I've got like 2 or more vectors, I don't typically draw them the same color, okay, if I'm doing it on the smartboard. For you guys in pencil, it doesn't really matter. It's all going to be in black, okay? But for my purposes, I always draw them in different colors just so it's obvious which one's which. They didn't do that here, okay, but that's fine, okay? Then we have a second vector, right, that is 125 meters after that. Okay, so this is typically then how we would represent 275 plus 125. Right, so what's our total? 400 meters east. Okay, always got to remember to have that vector on there. All right, so we drew them tail to head. First, this one happened, and then I drew the tail of the second vector, the 125, on the head of the first. Okay, continuing on after that. All right, everybody okay with that? What if instead of going 125 meters east, it went 125 meters west? What would it have looked like then? Yeah, I just go backwards. Yeah, right. I draw it tail to head. Here's the tail. Okay, going that way, 125 meters. Right, I still draw them tail to head. Sure, they overlap a little bit. That's okay. Lots of times vectors overlap or cross each other and things like that. We just have to be ready for that. Okay? It's okay for them to do that. Okay, everybody all right with how that one works? You've done, like I say, you've done collinear vectors before. This stuff is all in your notes, okay? But okay, it is stuff you've done before. So all vector addition is done with that tail to head method. That's what's really important, okay? The tail to head method is always what's used. All right, now I got perpendicular vectors. See how quick we get the perpendicular. Now I've got one that goes east and one that goes north. Still drawing them the same way that we did when they were collinear. So now I've got my 275 meter east vector, okay? And now I'm putting on the head of that 125 meters north. Okay, and again, remember, length represents magnitude, and scale can be important. Okay, because I oftentimes have people and they don't really take their time with their diagrams, and when we start getting weird angles and stuff, it's really important that you draw your diagram with scale in mind. You don't have to like measure it out and actually have a perfect scale, but if you've got a 275 meter long line and 125 meter long line and they look like they're the same length, your diagram is going to lie to you. Okay, if you're going to do all the math, you're going to look at your diagram and go, I must have done the math wrong. Okay, and that's usually not the case. Usually what people mess up is the diagram, and they look at it and it doesn't seem to agree with what they did, and so they doubt their math instead of their diagram. So make sure you have your diagram drawn at least somewhat to scale. Okay? If one line is supposed to be significantly shorter than the other, make sure that it is. Okay, and that's what we've done here. All right, so the car, or whatever it is, goes east, and then it goes north. Now, if I want to find the total displacement, that's the red line, okay? Because the total displacement is my change in position. I change my position from here, my initial position, to here, my final position. All right, everybody okay with that idea? So how do I figure out how long that line is?
A squared plus B squared equals C squared.
Exactly. Pythagorean theorem, a squared plus b squared equals c squared. All right, so that's my first step. Find the magnitude of my displacement. All right, so that'll be 275 squared plus 125 squared. Okay, so the magnitude of my displacement is 302 meters. Right, that's only part of it, though. Displacement is a vector quantity. I need magnitude and direction. All right, which way is this pointing? Okay, north of east, northeast. Are those specific enough? No, I need the actual heading, which means I need theta. I need the angle between the red line and east, due east, okay? How am I gonna find that? No. You could. Don't use sine law. I'm going to caution you against sine law right now. Okay? I know a lot of you probably learned sine law. Sine law is not good for this. Okay? And here's why. There's basically no work to sine law. If you do it wrong, and unfortunately, most people do in my experience, you'll get nothing for the question because you'll have shown no work because you used sine law and did it wrong. Okay? So while sine law is good for math, it doesn't allow us to analyze this piece by piece. It just gives us the whole picture, does it for us, okay, and doesn't allow us to analyze it. When we're getting into more complex vectors, we're going to need to break them apart into, okay, when this whole thing happened, how far east did it go? How far north did it go? We can't do that with sine law. Okay, we need to be able to do vector analysis, and so we use sine, cos, and tan. We use basic trig functions as opposed to sine law. Yeah, I mean, at this point, we could use any of the trig functions because we also know the hypotenuse. But I calculated the hypotenuse. And in case I messed it up, it's probably better to use the two sides I was given by the question. All right, so that's going to mean I'm using the opposite side and the adjacent side to get theta. Okay, so tan of theta equals opposite over adjacent. Okay, I'm looking for theta, so that means bring tan over. Okay, so theta will be tan to the minus 1 of the opposite side, 125, divided by the adjacent side, 275. Okay, so that angle is 24.4 degrees. Which way? North of east, right? Okay, and here's how you tell if it's north of east or east of north. That little angle arc that we always draw, whatever main compass direction it's touching, that's the of. Okay, it's touching east, we're going some direction from east. Okay, in this case, north of east. Everybody follow me there? Okay, so this is 24.4 degrees north of east. So our final answer then, okay, would be that the total displacement is 302 meters, okay, at 24.4 degrees north of east.
So if we just like accidentally use sine law because we're on like autopilot or something, will we like lose marks even if we get the right answer?
If you get the right answer, you're good. Okay. If you get the wrong answer, yeah, okay, then there's not much for me to go, well, where's all your method? There isn't any because you used sine. Okay. And again, the big deal isn't so much about that, it's more about when we start analyzing and breaking things down, especially projectile motion. Sine law doesn't allow us to analyze the parts, it just gives us the answer. Okay, which is nice, but it doesn't allow us to analyze. Yeah, it's not as useful. Okay, it doesn't let us see kind of the big picture. Okay, math's all about the answer. Physics is about the method. Okay, how we get there. Okay. Questions on how that one worked? Okay, is that pretty straightforward? I mean, it's just right angle, triangle stuff. And guys, honestly, all the vector addition stuff that we do is all about making right angle triangles. Okay, that we can find the horizontal and vertical components of, or east and north, or west and south components of, okay, and then being able to add them all together in the end, okay, that's what we're looking for. Okay, so that's what we just did there, okay, that's just written out neater. Okay. All right, try this question about the most boring town in the world. It's a vector addition question, but it's really easy. Okay, so let's go over this one. This is like the weirdest race I've ever heard of. Okay, go forward, untie some knots, and then solve the puzzle. Okay, so it says by adding the vectors graphically, basically that means draw a vector diagram. Draw these values tail to head. All right, so there's 10 meter long vector, okay, and then to scale, there's my 5 meter vector. It's about half as long as my 10 meter vector. Again, I'm not going to bother to measure it out. As long as it's close, okay, it'll be good enough. And then our 25 meter long vector. Okay. All right, so 40 meters to forward. That's all we have, it's just forward, that's our direction. 40 meters forward. Okay, super easy. Okay, that's just drawing them tail to head. All they really wanted you to do is draw the vectors somewhat to scale for that question. Okay. Now, I would like you guys to try number 7. There's a math trick to number 7. I'll give you that tip right now. There's a bit of a math trick to number 7. Okay? I would never give you a question like this on a test, but it's good to make you think a little bit. Okay? Draw the pictures. That'll kind of help. It's hard to fully draw them because you don't know all the arrows, but you'll get an idea of it. Okay. So, here's what we got. First, the car goes 500 kilometers north, and then it turns around and starts coming back south. Okay? And when it's all said and done, it's 50 kilometers north of where it started. Okay? So how far south does it go? 450 kilometers. All right, so the 3 segments in question add up to 450 kilometers south. Everybody okay with that idea? Okay, so that's kind of the first thing. All we did there was kind of use the displacement to figure out, okay, essentially how far south we went. All right, so here's what we've got. We know that the first one coming south is the one we don't know. Okay, it's the length we don't know. Then the next one is that plus 50. And the next one is that plus 100. Okay, so this one's x. This one's x plus 50. This one is x plus 100. All right with that. Okay, so algebraically now that this is graphically, algebraically, here's what I know. 450 equals x plus 50 plus x plus 100. Okay? They all have x, that first one in common, right? Because it said to us here, each of which is 50 kilometers longer than the previous one. Well, the first one was x. The second one's 50 kilometers longer than x. And the next one's 50 kilometers longer than x plus 50. So x plus 100. Okay? Now, I want to isolate x because that'll allow me to figure out how long each of the segments are. Agreed? Okay, so I'm going to then move the numbers over to the other side. I'm going to move the 50 over and the 100 over. Okay, by doing what? Subtracting. All right, so 450 minus 150 is 300. 300 equals x plus x plus x. In other words, 300 equals 3x. How long is x? 100. All right, the first segment was 100. The second segment was 150. The last segment was 200. That adds up to 450. Okay, it's a math trick. Okay. Wasn't really a graph. Wasn't really a vector addition question, but kind of. Oh.
That would kind of just like look at it and figure out it was 100.
Yeah. I mean, especially if you have a really logical mind, yes, you definitely would have come up with it. I'm just showing this is how you would mathematically solve it.
Not be fine for a test though, like you could just have the answer like that, but you can show how you got it.
Again, the big thing with just writing down the answer on a test is it's fine if you get it right. But if you don't, then I can't give you any part marks, right? And that's always the risk you take if you don't show your work. Okay. All right, try number 9. Okay, not a mathematically challenging question like the last one. So for number 9, the displacement part is really easy, okay? Because displacement is final position minus initial position. The final position is 2 meters. The initial position is 10 meters. Okay, so we got negative 8 meters, okay, or 8 meters down as our overall displacement. Okay, we don't even really need to draw draw a diagram for that. What we actually need to draw the diagram is for the scalar part, because people will often forget parts of this trick. Okay? The ball falls from 10 meters to the ground. Then it bounces back up 8 meters. Then it falls back down that 8 meters. That's what people forget, this part about it coming back up. Okay, they'll forget half of this. Okay, then it goes back to 4 meters. Falls 4 meters, and then comes back up 2 meters. All right, so we got 10 plus 8 is 18, plus 8 is 26, 30, 34, 36 meters. Whoa, not 3, 36 meters is our total distance traveled on that. Okay, people often forget the up and down part of the bouncing, okay, when they do that question. All right, questions on number 9. Okay. Here's your first one that involves more than 2 vectors, and it's perpendicular. Okay, so draw it out, make sure the vectors are tail to head and to scale when you draw it, and see if you can calculate the displacement, magnitude, and direction. You will have to do a little bit of trig because it does end up being a right angle triangle. Okay, I'm not going to go through the whole thing, but I'm just going to draw the diagram so you can make sure you've got the diagram right. Okay, so it says here that first she walks 0.8 kilometers south. Okay, then she walks 1.2 kilometers east. And then she walks 0.3 kilometers north. Okay, where would I draw a line that would represent her total displacement? Okay, well, our displacement is our change in position, right? This is my initial position, and this is my final position. My displacement should be a line that connects those two places. Agreed? Okay, so that line is my overall displacement. It makes a right angle triangle. That has a horizontal or easterly component and a vertical or north-south component. Okay? I should be able to find out what x and y are, and that would help me to get my overall displacement and the direction. Give you another couple minutes and see if you can get that before I do it. Okay, how long is x? 1.2 kilometers, right? Basically what we're doing is we're breaking down her trip into east-west and north-south components, okay? We know that when she gets over to here, she's 1.2 kilometers east of her campsite. She's also going to be a half a kilometer south of her campsite, okay? How do we figure that out? Well, this is a rectangle, okay? She goes 1.2 kilometers east in this rectangle. She goes 0.8 kilometers south and then retraces back 0.3 kilometers north. That means that y is 0.5 kilometers south. Okay, everybody all right with that? This is what we call vector component addition, and it's what we're going to be moving into tomorrow when we're looking at lots of angled vectors. Okay, now that I know the two sides of that triangle, now I can use Pythagorean theorem to get what d is, okay, or at least get the magnitude of it. So we're going to have the square root of 1.2 squared plus 0.5 squared. All right, so that's 1.3 kilometers in length. Okay, I still need the direction because displacement is a vector quantity. Okay, and I've got all three sides, but tan is my favorite trig function. Okay, so I'm going to use tan to the minus 1 of the opposite side, 0.5, over the adjacent side, 1.2. Okay, and that will give me my angle. All right, so it's 23 degrees. Which direction? South of east, right. My angle arc touches east and I go south of east. I could write this answer, okay? First off, I would write it like this, because it's the way I calculated, 1.3 kilometers at 23 degrees south of east. But I could have also written it like this, D equals 1.3 kilometers at 67 degrees east of south. Just means that I drew the triangle this way. Okay? If I draw the triangle that way, I get the same numbers, I just get a different reference direction. I reference south instead of east. Okay? Are they all right with that? We're going to be moving into more of that stuff tomorrow.
How'd you get 23?
Are you in radian mode? Yeah. Make sure you're in degree mode. You got to be in degree. Okay, everybody mask up and clean off the top of your desk. Grab a paper towel and you come around and spray down everybody's desk here.